Good morning, good afternoon, good evening, or good day, as I say in Australia. It's Juancho here. We're going to be talking about camera systems and the debug toolchain that I've added to the engine, which is going to make the development of your games a lot easier. But first, an announcement. I have released the literature review. It's officially called Class 100. This is a pass-fail assignment. There's no code. What I want you to do is to find an academic paper on game engine technology. It's a wide open task. What I want you to do is find something that you're excited about. I want you to present a 10-minute video. And then after everyone has submitted their videos, I will ask you to watch two of your classmates' videos. I will assign what video you're going to be watching. The key dates are that I need a paper proposal due date, and this is submitted to me in your Class 100 repo. You will put in the submission directory, you will fill out the paper I would like to review, and you're going to have 3 papers in here. Put them in order of priority. In most cases, I will give you the first choice that you picked. I do want to make sure that no duplicate papers are published, so it's first come, first serve. So if you get in early, you have a higher probability of getting that video. As I said, so 3 videos, and I will give you your top pick, or if for some reason I don't do it, I'll give you one of the others. Okay. And then the peer reviews. This is not a review, but it's a summary. You're not going to be evaluating each other's videos, but I want you to watch the video and then write up a summary of what the paper presentation is. So you will be submitting 2 peer reviews, and there's templates for those in your GitHub repository. And the dates are June 22 is when you pick. By June 22, you have to pick your paper, so you've got 3 weeks to do that. Then July 13th, you will upload your video to Canvas, and then July 20th, your peer reviews will be done. Okay, and this is a pass-fail assignment. So if you record your video and you do the 2 reviews, you pass. If you don't get any of these, then you get 0 for the grade. Why start early? I want you to explore. I want you to skim some of the papers. There's a whole bunch of links in the assignment on the web page and in the exercises on the assignment. You need to pick 3. The professor, that's me, will approve 1. 10 minutes. You'll probably have to do it a couple of times. You can use ECS, rendering, physics, AI, networking, procedural generation, animation, anything to game engines that we haven't already covered in class, or a paper that introduces some of the topics that we have seen in course, right? So there is a source list in the in the exercises, but you don't have to pick from there. You can pick from anywhere you want. Just add the link so I can go see the paper, and then I'll be able to approve your selected paper. What makes a good paper choice? This is a technical course. We're talking about the technologies involved in making game engines. I want you to talk about game engines. A 10-minute video is not just like a 1-paragraph article, and I really want you to pick something that we haven't done in class. So yeah, start browsing there. I see that 3 people have already downloaded the repo. That's great, and it's exciting. It's one of my favorite parts of the class is to watch the videos that you all make. Okay, so let's talk about the learning objectives for this course. So I had a couple of students ask me about the coordinates of the screen being tied to the window itself. Um, and I asked them to wait until we got to a future lecture, and this is the lecture. So today we're going to implement a camera system that transforms world space positions into screen space for rendering. So we're going to have worlds that are bigger. You will understand what the relationship between world coordinates and screen coordinates are. And then you will see an implementation of a camera pan and zoom system. And basically, we are going to have a camera input structure and a pure free function that does the mapping. We're going to work on we're going to build our world based on a data file now. And then you will be able to see the debug pause. So in our game loop, we can pause our game by not calling any of the systems and only call the rendering system. And we'll see how that gives us the ability to pause something and examine. We're going to split our HUD into a game HUD and a developer HUD. And then I will introduce you to the debugging system that allows you to inject keys, dump the state of your game, and then trace, so you can go through and see what is going to happen in every one of these sections. And then I've also provided you with an interactive debug session builder. These keys allow you to build up a set of commands that will start the game, run something, click some buttons, and then quit, so you can examine the status. And that way you can use your debugger, and also additionally you can feed those dumps to the LLM and ask your large language model assistant to help you debug. Okay, so those are the learning objectives for today. So some of you asked me a very smart question. You asked me why we had our world be exactly the same size as our screen. The reason was that I hadn't been able to introduce you to a camera system. So what we're going to do today is we're going to allow you to have the world of an arbitrary size by introducing a camera system to our world. So what are we thinking? Let's say we want to have a large adventure space, some sort of game where you're wandering around this large field, but you want to have things happen over here, and then you want to be able to kind of look around it. And this is how we're going to do it. What we're going to do is we're going to define here that our world will have the center as 0, 0. So this is the center of our world. And we're going to say that positive x takes you to the right, and positive y takes you up like that, right? So that's our world, and this can be an arbitrary size. You can have, this can be huge, it can be small, it doesn't matter, right? What we need to do is also think about the screen space. Our window, once you start your game, you have a fixed size. You can resize it. We'll deal with that later. But for now, let's assume that we have a device that has a screen of 800 by 600 pixels. You can change that in the data file. You'll be able to see that. And we're also going to have 0, 0 at the bottom left-hand corner. And our render system will draw entities in these positions, right? So somehow we need to convert points that are in this side over to this side. So the way that we do that is with a camera system. So the camera system is going to have the following properties. Camera is going to have a look at. So in the kind of default setup that we're going to have, and we'll change it, don't worry about this, is we're going to have a world that is 800 by 600, right? And what I'm going to do is my default view is I'm going to have a camera that has a look at of 0, 0. So I'm going to say the camera is looking here. So this is where my camera is looking, right there. And this is my camera width and my camera height. And I'm going to have a zoom of 1, right? And so in this particular case, we're going step by step here. We will get to larger worlds and smaller worlds. But for now, let's go with a world that is kind of the same size as our screen, but it's offset. So in the world, I may have a value of 0, 0. We're going to change colors here, and then we'll go through that. So now, our zoom is 1. That's how much we zoom in, or is exactly like zooming in with a camera. And pan here is when we move our things around. And I'll show these all to you in the game in just a second. Here we have the math. And the math for this is fairly straightforward, and we'll go through and put some numbers into this. But basically, we need the camera left. So the camera left is this value here, right? And it's basically, I'm saying I want to have the value here. So this is my camera left. So it's minus, so camera left is minus 400, right? We can go over here. You'll see that the camera left is my look at 0 minus the camera width, which is 800 divided by 2. My zoom at this point is 1. Because we have our default camera with zoom 1 here. Okay. So once we have set up our camera left and our camera bottom, and we know what our zoom is, we can immediately calculate the value where this object should be on the screen. So let's put some numbers in here. Let's have a look at our default camera with a zoom of 1 on an 800 by 600 window, right? So my camera width is the width of the world divided by the zoom, which is 800. The camera height is 600. My camera left is 0 minus 800 divided by 2, which is this value here. And then when we go back here, we see that this is our calculation for determining where something in the world lands up on the screen. So if I have a position at 150, let's go over here. So what did we say that was? 150 in the world. So let's see, this is 1, 2, 3, 4. So we're looking for 100. So it's going to be, so this is 100 roughly around here. This is 100 is along this line, and 50 is going to be along this line here, right? So this is the point we're looking at right here. That's the world, but we want to know where it's going to end up in the screen. And so basically we apply this math to it, and we get 500 and 350. And so if we go and we use green for our screen space, so our screen is 0, 0 here, and so we said that this number is 500. So if I go over here, I go, this is 400, this is 500, okay? And then I go along here and I go, this is, what am I looking for? I am looking for 350. So I go up here, I go, this is 300, this is 300, this is 400, this is 350, and so go across there, and you'll notice that they are in exactly the same position, except the green point is 500, 350, and the red line is 100. The red point was 150. So that's how it works. So the camera is going to have this abstraction, right? We're going to have a look at, we're going to look at, we're going to, where are we looking and what are we zooming? And for now, we're actually going to just have the width be 600 and 800, 800, 600. So the screen position, which is the camera output, the screen position placed HUD elements at fixed screen locations. The camera system writes a screen position for every world space entity, right? So basically, we are going to have a system which is going to produce this for our entities. So now we are going to be able to define our entities. So I could, if this red thing here was a element in my world, I would say you have the position of, I believe it was 150. In my world, I can do all my logic around this thing because I know that my origin is there. However, when the render system sees the value for this entity, it's going to see 500 and 350. So the render system sees this, and all of the game systems see this value here. Okay, let's dig into the camera, how the camera is implemented in our ECS state. Let's go to this slide first. So the first thing that our camera system needs to do is we need to get our values for look at, zoom, and then we also need the width, right? If you recall, we have the look at position here. We have a zoom, which kind of shows us how much we're zooming in, just like a camera. And then we have the width, which is this value here, and then we have the height here, right? So we need all of those values for our camera. So we get those. Those are all going to be in the blackboard. We have this read float function here, which is defined here. I'm not going to explain it, but this is a defensive read. So we're reading from the blackboard. So if for some reason we don't have the key, then we try to get the float for the key. Otherwise, we're going to return the default value. So this function is called with the key and also with a default value. So basically, it's kind of safe programming to say, if for some reason the blackboard doesn't have the value for this, set it to 0, 0, and set the zoom to 1. And then integers are a little bit easier to deal with. Our blackboard can deal with those easier. Our camera width is then, as we saw before, it is the width of the window divided by the zoom. The height is the window height divided by the zoom, and then we calculate the left and bottom values of our camera, because we need that in the next step. So what we are going to do is we're going to look for all of the entities that have a position and that they also have a size, right? Then once we have that, we get our, we calculate our screen value right here, and then we add a component, screen position, to our entities. So our gameplay values are the position, right? And that's what we're going to do our calculations on. Now we're no longer going to do our calculations based on where things end up on the screen. We're going to do based on the world that we've set up. And so notice that we're dividing the responsibility. So the responsibility of tracking where something is in the world depends on the position. The responsibility of where it's going to go on the screen depends on the screen position. So here's our world. In our game data.json, we define our world to be like this. and then these are stored in the blackboard as world X, etc., etc., right? So let's have a look at our world. Here's our world. It's been sitting there patiently running for now. I can do the following. I can zoom in. So I'll zoom out, I mean. So if I've done that, so now you can see, so the zoom has changed. I can play my game. Notice that my little guy doesn't leave the world, but the world is now zoomed in. I can also zoom in to this guy. I can go in and get a really good close up at him, and I can pan around. So I can go around like this. And so what these commands are doing is they're using this. When I do this, I'm changing the look at point. When I'm doing this, and then when I do use the minus sign, I'm changing the zoom, so I can zoom quite far out. That's as far out as I can go, and then I can zoom in, and I can get this information. So I can go in and see, what does my guy actually look like? So there, that's what my guy looks like. And so here he moves really fast relative to the screen. And then if I go all the way out, I can actually do the same. I can move out while I'm zooming around. So now, as per the question that some of you asked previously, why is our world the same size as the screen? It is no longer the same. We now have this capabilities. I added this multicolored outline so you can see where the world is, and so you can do like that. Okay. So that's what is happening there. We can define our world boundaries. So we can change the game data. As you can make your world larger or smaller. It's going to map to the screen in the correct way. So as you're thinking about designing your game, you can actually think of larger worlds than you would right now. Okay, so now that we have the math that allows us to do all of our camera stuff, so we've gone through, we've figured out the math for this. So here's our math, right? We have the math. We walked through some examples. We're doing that. And so now what we can do is we need to implement our camera control system that I demonstrated to you, and I will demonstrate after we do this. So we've got all of our world set up. Now let's think about how we're going to do our camera controls. What we want to do is we want to have a camera input that is decoupled from hardware. So the way we're going to use that is if we go here, so we have a camera control system, and what this is going to do is we're going to we have our equals, our minus. So this is plus, this is minus. We don't care whether it's plus or equals. We're going to zoom in on that key regardless of whether it's plus shift or not. Minus is the same thing, and then left is WS. So left is A, right is D, and so what we are doing is we are building a Boolean map. So we have this camera input that has 6 Boolean members: zoom in, zoom out, pan left, pan right, pan up, pan down, right? And then we call this function here on camera control. So this is a system within our game, but it's not actually processing any entities. It's just preparing the data for the camera control, which will go and map our world entities to our screen entities. So let's go back and have a look and see how this is all doing. So our camera input structure is this one here. This is what we're filling out. And so the reason that we're doing this independent from STL is so that we can unit test our apply camera controls. We have some constants in camera control system.cpp. I would encourage you to go in and play with those constants and just see what's happening. Zoom speed and pan speed are multiplied by delta time. We talked at the very beginning about how to get consistent movement in our game we define our speed as pixels per second, and then we multiply it by delta time so that we have a consistent speed. We do the same thing with zoom speed and pan speed, and then we're also going to have a min zoom and a max zoom, stuff like that. We don't have min and max pan, so you can actually go off the world and not find yourself again. The apply camera controls is going to go through and read float helper. That basically, this is our read float again. We saw that earlier. Again, go and ask ChatGPT about that. We get our delta time, our camera zoom, our camera look at, and our camera look at Y. And then we apply our zoom logic. So if we're zooming in, then we're going to take zoom is going to be plus, we're going to add to zoom the zoom speed times delta t, and if we're going out, we're going to subtract it. And what we're going to do here is we're going to make sure that we don't zoom in too far or zoom out too far. And then the pan, again, we're going to do here, we want to make sure that our panning is independent of zoom. So basically, we divide here by zoom so that our panning feels the same at any zoom level. Let's go have a look at both of these things in our game now. Let me just restart this game. I'll restart it. Restart the game here. Okay, here's our little guy about to go on his adventure, and so let's let me zoom. Let me show you the panning. So I can pan this way, I can pan that way. You can see how the speed of the pan feels kind of the same speed. Now let me zoom in. And now you see that the panning feels the same. And now let me zoom out all the way, and you'll see that my panning kind of feels the same. So I don't get a really big difference in panning. I would recommend that you go in and you play with this, take this dot zoom out, and then see the effect that you get when you do that. Okay, so that's, play with the code. Just go in and start playing with the code. I want you to read a lot of code, and so now that we're getting into these systems, take the time to go read them. Make sure that you're getting your money's worth out of this course, not just getting the grades. Okay, so let's go here. My apply camera controls, we compute the values, and then we just set them back again. Okay, so that's what we've done. So what we do is we get all of our value, that we get our delta time so that we can multiply our zoom in and zoom out and pan. We get our current look at and there, and then we go here, we apply our zoom. We just change one value, the zoom, and here we are going to update look at X, look at Y, etc., etc. And then here we write them back to the blackboard, right? And so, as I said before, this is our update. This is a system. It's a camera control system. Notice that we don't hand the components into it. We're just handing the blackboard, because this system doesn't impact the entities at all, but it is a system that runs in our pipeline. And so let's see, what do we do? We've done the D. I've done all of this stuff, but let's go do it again. We will do this. So here's my panning up and down, zooming in, zooming out. So here am I zooming in all the way. That's, I've reached my boundary, and here I'm zooming out in all the way, and that's as far as it goes there. And now I can go over here and find my guy, and I can see that he's got a little green shirt on. So that's kind of cool. Okay, next we'll talk about debug, pausing, and stepping. When you build a large when you're starting to build the game engine, you also want to provide tools for the developers such that they can inspect what's going on and understand the logic of the systems that they're building. And so we're going to introduce some debugging tools in the rest of this lecture. Okay, so we've talked about the camera, world coordinate systems, and we have local coordinate system, and we have a camera that ties the two together. Okay, that's great. Now you can have large worlds. What we also need is some tools to help us understand what's happening within the game. So what we're going to do in this particular section is, for the rest of this lecture, is we're going to introduce you to a four-layer debug toolchain. First one is we want to pause the game. The second is we want to be able to display debug information in our game while it's running. And then I'd like to be able to introduce you to the ability to automate the testing of your game, such that you can test your game without having to sit there and click your keys, etc. Right? That's what we're going to do. First, we're going to investigate these and see how we can do that. So let's go here. Let me show you what we're talking about here. So here's my game. Here's my game. It's playing. As you can see, the little Intrepid Explorer can run around. Now I can hit F10, which brings up my HUD. If I hit F10 again, it goes away. Now I'm going to hit F10 and hold it, and you'll notice that the HUD is still there. Now I'm going to hit F1. Notice that if I'm going to hit F2 now, and it'll advance one frame at a time, right? Now, what is important here is that I hit F2 and I hold it down, it doesn't keep advancing the frames, right? That's not the behavior we want. We want to be able to tap F2 and it increases by one frame, and then F1 allows it to run again. Now my Intrepid Explorer can run around. F1, now I can't do anything if I hit the controls. What's happening here is that all the systems are not running, and when I hit F2, they run exactly one time. That's what's happening. Okay, so we're going to have some variables, but we're going to add these variables into main, right? Debug pause tells us that the game is paused, and we're going to toggle it with F1. F10 is going to be the debug HUD visible. It's also going to be auto-enabled by when F1 makes this true. We have a variable called step requested that we're going to set to true for exactly one frame. And then we're going to use these keys here to enable very precise control of these toggle keys. So let me explain this to you first. We're heading towards this code here, should toggle, right? So let me explain this with a diagram, and then it will make sense. So let's say that we have a signal, right? We have a signal which is a key that has been pressed. So if it's not pressed, so if this is false up here, pressed is false, so this is pressed. And then we go along here, and then we drop down here, we press the key, and so now the value, so if I have P for pressed, and these are my frames, 1, 2, 3, 4. Let's have this guy go up here like that. 5 and 6. Okay, so the value for pressed, we need this as a truth table. So this is false, false, false. Sorry, true, true, false here, right? So my key is pressed for 2 frames. So I could write, and I want to toggle this value T0, right? So I could, if I don't think about what's going on, I could naively write the function, this value here, if P, then T0 equals right? So what I'm going to do is um, I'm going to toggle when P is pressed. I'm going to toggle, but there's a problem with that because what's going to happen is that this value will toggle once in this frame. It's going to toggle here, and then it's going to toggle here. And so when I let go of my key, if you think about it, I have at this point let's say T0 is equal to false. Okay, we're going to initialize it to that. So when I come along here, I go, okay, this is false, this is false. Okay, here I go down and I set it to true. And then here I go down and I set it to false. And then I go along here and I keep going, right? So the problem is that the value of T0 at this point here should be true, but because of this second trigger, and because we wrote this code here, we have basically ended up with a value of T0 that is not correct. So what we're going to do is we're going to add another variable. We'll make this one a red variable. Okay. And so I'm going to call it was pressed, right? And so we'll draw our line along here for our truth table. So was pressed is false, 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 true, true, and false. Okay? So now let's have a look and see what we can determine here. So notice that here we have was pressed is false and this is true. So we want the value here, we want this value here to be true, right? So I don't want to have P here. I want to replace this with something else. So I want to write the code. Let me go back to white here. Oh no, we could use the red code. That's fine. So I want to write if something T0 equals not T0, such that it doesn't happen here. It turns out that we can use not WP and P as our triggering condition. So if I say not WP and P, then we have, so we'll call this the should trigger. Well, this is should trigger. We're going to call this, the result of this is going to be, this thing here is going to be should trigger. Let's go through the truth table and see what we have. So we're doing not WP and P. So and P, this is false, this is false. So this is false here, this is false here. Here, not WP is false, and pressed is true, so we're going to get a true here. Then, was pressed in this one, was pressed is now true. So not was pressed is false, so this becomes false, and this becomes false, and this is false here, right? So what we've done is we've identified the precise frame where we should toggle this key. And this is a standard practice in kind of high-performance engines where you do this kind of processing to make sure that the event is triggered only once. And so that's exactly what we're doing here. That diagram was exactly preparing you for this. And so if we are, so basically now that we have this, we can go, okay, if we are paused, so if we are debug paused, remember debug paused is a variable that says our game is paused, and then here is our previous and our current, and so basically we're going to return debug paused and should toggle so that we get the exact point where F2 is pressed. When we one of the requirements that we had was that when we press F1, we make the debug HUD visible. So that's what we're doing here. This happens after we've decided to toggle the pause. And then for our step complete here, we're going to we're going to have a function that takes two parameters, step completed and debug paused. And so I'm going to be apply step complete. So I set the step complete to be false. And in order to avoid a compiler error, I use this variable because the compiler will complain that I haven't used that. But basically, I don't change the debug pause. I do change step requested, and the game will stay paused, but it will exactly run by one step. And then so what we're going to do is, remember when we did the timer, we spent a lot of time calculating how much time had elapsed since the last time. Well, if you're in this position here where you're paused and then you hit F2, you don't want to advance your game by 10 seconds. So what we're going to do is we're going to pre-compute our target FPS. We're going to basically say, okay, in this case, we are in a unique situation. We are debugging our game, so we're going to pass in 1/60th of a second. So our target FPS is going to do that. So our step delta time is always going to be exactly 1 over the frames. So all of these functions live in debug state.hpp. Go ahead, read them and understand them, and again, use Claude to help you understand them. And so now, let's see what our game loop looks like. Again, go into the game and have a look at it. So basically, we get the state of our keys. We set is pressed for all of our keys, and then we basically go in here and we say, is F1 pressed, F10 pressed, and then we basically say step requested, right? So all of those functions that we use there, we're now using here in main. And so when you see all of this stuff in main, you can reference back to all the work that we did here. And in particular, you can go back and look at this truth table and see why we have this capability of hitting the key and something happening immediately for that key, but not repeating. So it's independent of key repeat. It's just the event happened in this frame here, and so we're going to either toggle, etc., etc. Okay, so we've set all these variables up. Let's see how they're used now. First thing to do is to gather the information. We read the hardware. We use STL to read it. And then we decide on whether we should toggle. Should we toggle the pause toggle, the debug HUD visible, and should we set the step requested? Okay. Now, in our game loop, we need to adjust our game loop a little bit to make sure that we're doing the right thing. Okay, so what we're going to do is the following. Our game loop now has to determine what's going on. So if we are debugged, so if we're not debugged, if we are not paused, we're going to skip through here, or if a step was requested. Now, when a step is requested, we need to do two things. First of all, we need to trick the system into believing that 1/60th of a second has occurred since the last time the simulations ran. So we're going to do that here. And then we're going to, at the end, we're going to apply step complete here. We're going to undo step requested. So this is going to set step requested to false. And then the timer, basically, if at the end of it, I will update my timer end frame. I will actually update my, so if I am running, then I run the end frame, and if I am executed a step, I will do timer end frame. Otherwise, I call timer end frame no advance, so the frame counter counts simulation frames, not wall clock frames. So the pause, so this here doesn't update the time inside of the timer. Okay, so let's go back and do the demo. No, we're not going to do that yet. That's a demo for later. Let's keep going here. Okay, so the debug hub overlay, that's coming up next. Okay, let's talk about the next debug tool, which is our HUD overlay. This is fairly straightforward. We are going to basically have a debug HUD system, which is very similar as a render system and the HUD system that we introduced before. So we'll go through this fairly quickly. We're going to take a renderer, we're going to have a resource manager, and then the window width, height, etc., etc. Then we have a dependency injection construction pattern. We're going to store these as member variables, not singleton, so that we can add this as construction. The debug overlay draws a full screen semi-transparent rectangle before the text, and alpha comes from the game data.json, so you can change the alpha there, and then you go through. If you want to understand what all of these STL render modes are, go and understand it, but you can see the visible for that. And then the render method takes 3 direct parameters, not blackboard values, because the debug state lives in main.cpp. And so we're going to take the render. It's are we visible, are we paused, and the frame count, right? So we're actually not going to give access to the blackboard to this system. We could if we did, but we've chosen not to do that. After positioning the method, we basically render the status line in the frame counter. Yeah, we're going to, it's basically, and then we have to do the y-axis flip. This is a reminder from our HUD from previous lesson. And then the HUD toggle behavior is between F1 and F10. So we have this 2 toggle paths. Both of these are using rising edge detection that we talked about from should toggle. So F10 toggles the debug HUD visible independently, and F1 automatically turns it on, right? Unpausing does not hide the HUD, it leaves it there. So now I've showed you the demo for that, but let's do it again just for fun. And so here we are. Here's my, I'm going to do F1, F10. So there we are. We're playing our game. We can continue to search for gems in this scary world, and then we can hit F1 and it pauses, and we hit F1 again and it keeps going. Notice that we have made the decision to leave the HUD on. You could actually modify it such that when you unpause it goes away. It's entirely up to you. You could do that, but anyways, F10 always turns it off, right? And so that's our HUD. Again, it's went over it fairly fast because it's basically a repeat of the HUD that we did before. But go in and read the code and see how we're doing it. You will be using the debug HUD as you debug your game in the future. Okay? Okay, so I introduced this in my course last year, and it was very useful. So I've improved it this year. What we're going to do is we're going to solve the following problem. When you're running a game, something happens at frame 47, or something might happen at frame 2000 or 27,000, might happen quite a while into the game, or you've had to press a whole bunch of keys in order for something to happen. So let's say you wanted to fire up the game and then go right, and you wanted to see what happened at the beginning of the game and what happened at the end of the game, and then you want it to stop automatically. What you can do is the following. You can run the game. We've built it such that you have these parameters. It processes these parameters. So the keys are all of the keys that are going to be injected into the game at the frame number. So this is saying at frame 2, frame 3, following frame 1, insert the right key. This here says I want all of the data of the game that was at frame 0. So how did the game start? And this is how did the game end? After I have 3 frames, what does the state look like? And then this says, yeah, after frame 5, just stop, right? And so basically, we can use this to run tests and have the game run for us, which is kind of fun. Also, you can take those files, I'll show you where they are in a second, and you can hand them off to the LLM, and it can be incredibly powerful finding patterns in those files to help you diagnose which one of your systems has done something correctly or not. So, why? Oops. So basically, we are going to have, so the substructure, the structure that we're building here is we're going to have a key action. We're going to store this information of the keys. I'm defining a number of keys that are valid. As you know, when you are building your game, you might want to add other commands there. And in the future, I actually add mouse clicks. So when we get into a later lesson, you can actually schedule mouse clicks to happen at a particular point on the screen at a certain frame, which comes in very useful in the tower control, tower defense game that we do in lesson 9. So you can actually have multiple keys firing on the same frame. The keys vector basically holds all of these informations. You can look at the CLI parser to see how this is all parsed. Then the command, all of these commands are stored in this data structure. I want you to go and read through the code for this so you can understand it. But basically we have our command line options are there. It's like, when are we dumping our frames? When are we tracing? I'll explain what the difference between dumping frames and tracing frames is. Stop frame. If you have multiple stop frames, it stops at the first one that it finds. There's no error. If you say stop at frame 10 and stop at frame 50, it'll just stop at 10. Any actions that you may have expected to happen after that will stop, right? So the command line parser is built into main. You can see it there. It just returns the options. If you have an invalid argument, it won't even try to fix it. It'll just say, "Oops, you made a mistake," and it'll print out an error. And so basically, main. What happens is that main looks for flags before it initializes it. So basically, main will try to determine whether there is some options that it needs to do, and if there is an error, it returns 0, and otherwise it keeps going. So let's go. The implementation's there, but what's fun is what can you do with these things, right? So you can start your game in paused mode, right? So you can start with, you can start the game so it doesn't advance, and then you can do F1. Then you can have verbose, so it will print out the detailed information to standard out. This is very noisy. You can clear the logs. Whenever you do a dump or a trace, it writes logs. You can use it with clear logs. This is the default. It just wipes out all of your logs. If you're trying to compare from one run to another, you can do the no clear logs. So basically you can, so here I can compare between two runs. So here what I'm doing is I'm playing the game. I'm dumping it at 0 and I'm stopping at frame 1, And if I do that twice, I'll get 2 time-stamped outputs. This is where the fun, but that's all. I don't use those that often, but this is the one that I do use, is something like this one, like I showed in the original example. So what is going to happen here is at frame 0, I'm going to dump. So all of these things get sorted according to the frame number. So 0, there's a dump. 1, 2, 3, the right key is injected and the player moves right. And then the frame 3, the dump state, right after the right press is in the game 5. And so there's a log directory that will contain 4 JSON files containing the ECS state for the frames. Then trace. Trace is one which is a heavy-duty dump. It basically does a dump of your game before every single system, so you can actually see what's happening in the game. Remember, we think about our game data as that blackboard in a room, or a large spreadsheet. And so what we're doing here is, when a system comes in and works on that large blackboard, we take a photograph, and then the next system comes in, we take a photograph, and then we take the next one. So each one of these is a state of before. So basically, before JSON is what happens at the very beginning of this frame, and then player control system runs, so we can see what player control system did, what it updated, which entities it updated, which changed, and then we can have all of this information. So it's quite useful. Part of the assignment is to play with this. We've implemented a JSON serializer that takes the complete ECS state. It's in JSON serializer.hpp. And basically, this is what your JSON files look like. You'll have your entities, the names, the positions, so you can go through and search through them. All of the key values, so the entities are stored like this. And then my blackboard is stored like that. So you can actually see what's happening frame by frame, if you choose to do it that way. Okay, so these flags are very powerful, but they're very tedious to build. So I've put together a little Python script that you can use to build out interactive or predetermined gameplay testing scenarios, right? So what do I mean by that? We are going to, if you go to, if you start the run.py on the game, you'll see the following. And so let's do it live here. So here I have the run game debug. See, number 3. So what I'm going to do is I'm going to pick number 3, like that. And you'll notice that I now have a debug session builder, right? And so here I can do a key press, repeated key press, a frame dump, a frame trace, a screenshot, and a set stop frame, and set frames per second, and a whole bunch of pause start, right? So let's do this, and let's make a little script that's going to make our little explorer run across the screen, right? So what I want to do is I want to add I want to do this one here. I want to have the little explorer run across the screen, let's say 50 times, okay? So let's do that. So I'm going to do 2, and I'm going to start at frame, I don't know, let's start half a second into the game, half a minute into the game. So I'll start at 30, and then I'm going to do write. I'm going to do write for 2. So it's going to insert write. And how many presses? Let's do, let's see, let's do 30. So we want them to run to the right for 30 frames, like that. And do we want to have any frames? Do we want to have any gap between them, right? And so we're going to say, no, let's just do 1. Okay, there we go. We'll do that. And so now if you look up here, you can see that we have added all of these. These are the events that are going to be injected into the game. And that's cool. So now um, let's um, let's run this debug session. So I do 14 like that. It's not the best user interface, but here we go. 14 it is. There he goes. He ran for half a second. Notice that I didn't put a stop frame in there, so I actually have to go and kill it. Let's put a stop frame in here. Where's my stop frame? 6. So I'm going to do 6. Let's stop the frame at, I don't know, 10 seconds, so 600. Let's make him do a little dance. So I'm going to do, so at line 59, he's stopped going to the right. So I'm going to go have him go to the left. So I'm going to do 2, add a keyframe. So we'll do 2. And we're going to start at, I don't know, 200. Yeah, we'll start at 200. And then we're going to make him go to the left. 1. We're going to do it 30 again. And we're going to make him go slower. So we'll do 2 like that. And we'll do 3. We'll make him go 3. So we're going to go slow. So now we're going to have him go fast to the right, and then we're going to go slowly to the left. Now I can run the debug session. So 14, here we go. There he goes to the right, waits, and he goes slowly to the left, and then we wait until we see the game end. It should end. There we go. And so that's it. So there's one more thing that you will find incredibly useful, and in fact it's actually required for the assignment, but this will be very useful for your development. It has helped me a lot. So when you have finished, when you've gone through and you've set up your debug session, you can actually save it as a script. So let me show you how to do that. Let me go find my terminal here. Let's get rid of this guy here. So let's run this again. Python run.py. Okay, so I'm gonna do. I'm gonna start at number 3, and then I'm going to add. Let's add the 50 key presses that we had before. So we're going to do 2. Start frame at 0, and we're going to go to the right for 2, like that, and we're going to do it 50 times. We're going to do 50 times over to the right, and then we're going to do 1 time every frame. And so now I'm going to add an exit. So I'm going to do 6, 6. I'm going to stop at 70, like that. And then I'm going to save, I'll run it. Let's see what it does. It's 14. I'm going to run it. 14, and then there you go. And it did that, except that's exactly what we wanted. Now, if you exit the Python program now, you will lose that script. But what you can do is you can choose option 12. So option 12, and you give it a name. Let's call it 50. And then you get to save it as local or distributed. Don't worry about that. You can just save it as distributed. Doesn't matter. Yeah, distributed. And now you can exit. So I've exited the debug mode. If I go into debug mode again, 3 here, if I run my debug session, there's nothing to do, right? Because there's no commands. So I exit. But what I can do is I can now go to option 13, and I can load my 50, so number 1, and then I can run my debug session like that, and then there he is. It's up, boom, exactly. You'll also notice that if you load the script 13, there's a reveal all gems, which is number 2. So let's try that one, and let's run that one. There we go. all the gems are revealed and I didn't have to touch a thing, and we're taking some screenshots at the end of that. And so if you quit, stuff like that. So you can examine the script that I left you there, and you can play with that. One of the things you'll do for your assignment is you'll find how many steps it takes to reveal the first gem, and then you'll be producing an image before and after that gem is revealed. Okay. Okay, and so the gem reveal game, it's exactly what you had the last time. So we've got the layout. Notice that what we're doing here is we're changing the layout of the objects here. So we now have the world, and so the world now loads from here, and our players are slightly different positions. Sorry, our player is the same sprite, but he's starting at -400, -250, and has input and velocity components. The 5 gems are now in different X positions because they're now positioned in the world. I've added 4 corner markets just so you can see things that are rendered but have no motion or no action to them. I have 3 HUD entities of FPS counter, score display, and controls to help text with the screen position. The entity they're set up in the JSON file, so you can see that there. Go ahead, play with it. You can change the positions now without having to recompile your game. The corner markers are set up in the file as well, and then the texture mapping, we basically have put that into our data file as opposed to computing it manually. So we've changed that. So compare lesson 30 to lesson 40 and see how these things have changed. So the texture mapping is loading into main.cpp, and then we do the same thing that we did before. There's the gem reveal system. We have a horizontal overlap, which we used in the last class. These are all being changed slightly to work in the world, rather in the new world coordinates rather than the old world coordinates. Then the camera is independent. It does not follow the player. The camera starts at the default position and only moves when you use WASD. So if you're zoomed in, the player can walk off the screen. Let's go have a look at that. cd dot python run.py. Let's do 2. So if I zoom in, the player's off there, so the player's going to come into the world, and we'll go exit the world, and now I've gone all the way there, and now if I zoom out, I'll see that the player is all the way over to the left, something like that. So that's, we can do that. We have the camera transform in there. Our movement system is basically the same, adjusted for world rectangle, not the, so we've changed the world, so there's some changes there. The boundary checking is now looking at the world range. The render system is now using the screen position rather than position, because the camera transforms. That's how the transforms that the camera puts in reaches the renderer. So we've done the demo. We'll do that. Okay, so this is what I want to do. I want to go in and say, basically, I want to change my assets. So if you go into here, Control C, let me just add 0. I'll do Cairo dot here. So let me go in here So what I want to do is go into my assets. Where do I want to go? Assets game data.json right here. And I want to change my world to 1600 by 1200. So I'm going to change my world size right here to 1600 by 1200, and I'm going to change my the x to be minus 800, and this is going to be minus 300, minus 600. I'm going to save that, and I'm going to run that game now. Python run.py. 2, I'm going to run the game. What did I do wrong? Two minuses there. Save. 2. And if I zoom out now, there's my world. So you see I've made my world bigger. Now the background texture and the placement of the objects within that world were based on the old world, but you can see how you can actually change your world, and you could place some objects over there, etc. Right? So you can play with this and rearrange things to see if things work in the way that you expect them to do. But this gives you a lot of freedom in terms of setting up your game and playing with your game without having to recompile, everything. Okay, so I need to go back here and I need to change this back. Let's go Control Z, Control Z, 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 Z. Save, and then go back here and then do 2 and run it again. And now we notice that the world and the texture is the same size. Okay, so where are we here? So we're going to talk about the exercises. I will be right back. Okay, we've wrapped it up. We've got camera and we've got debug. So the exercises this week are just intended to get you familiar with these. There's 4 of them. There's more details in the exercise document on the webpage, but here we go. Do some calculation. I want you to calculate a position just so you can go through and do the math. Do it by hand. It's fairly straightforward. But what you could do is run a debug session with -dump and check the screen position. So in the exercises, there's instructions on how many steps you should take to get there and how you should set it. That's all good. The second one is I'd like you to use the debug system, the CLI debug system, to build a script that goes and finds exactly at what frame that first gem is revealed. Every one of you will have a slightly different answer, which is fine because depending on your machine and the frame rate, it could be you'll be off by 1. Just do that. Play with that for a bit. That'll get you familiar with the debug construction system. The third one is we want you to kind of do what you did with the last class, is to update the HUD customization, but we want to add a line to the debug HUD, not to the HUD. So we would like to have that there. And then the fourth one is play with game data.json. I did that a little bit on the video. I want you to go ahead and just play with that and see what happens to the player, and then we can get an image for that, and then you'll be done. This will be a fairly straightforward kind of a reminder of what we've added. We've added camera, we've added a world system, and a camera that converts that to screen system, and we've also added some fairly interesting debugging tools that allow you to sample the data in your game and therefore be able to hand it in for assignment, etc. Okay, thank you. We'll see you next class.